Hi, my name is Denzel Carter, and this is Lab 5, Faraday's Law. So in this lab, we're going to be observing a magnet falling through an aluminum tube, modeling this in a computer, and then comparing the computation with the real model. And we can't use a Ferris tube because then the magnet would be attracted to it. So here's some physics principles I used in the lab, such as Faraday's Law on the right, which allowed me to find the induced EMF, Ohm's Law, which helped me find the induced current in the tube, and then the magnetic field equations due to a dipole are also seen on the right. Newton's second law is also useful to help find the acceleration, velocity, and position of the magnet. So for the observational model in real life, you basically just want to get an aluminum foil like this one, and then a bar magnet, and then drop the magnet through the tube, and then record 5 trials, and then take the average time taken to fall. And here are some of the measurements I took for the aluminum tube and the average time to fall, as well as some properties of the magnet that I found from Lab 3. So here's the computational model I used. At the first part, you can see where I put in the geometry of the tube from real life. The properties of the magnet from Lab 3 are below, and then the function to find the dipole magnetic field, and then the d flux over dt are below. So here I have the force due to gravity, the actual magnetic field at the ring using the dipole magnetic field function. And then below that is the net force on the magnet, which is just the magnetic force plus a force due to gravity. And then below that is where I use Newton's second law to update the bar magnet's velocity and position. So here's the computational model with the tube on the left, and then the velocity versus time graph on the right. And the computational time was 1.603 seconds, while the actual time was 1.282 seconds. So to the interpretation questions, the blue and red coloring corresponded to current flowing in opposite directions. And I found that the red coloring had to correspond to the counterclockwise direction, because at the bottom of the loop, the current is red, and the tube is trying to keep the magnet from falling at the bottom. And what would happen if the magnet was flipped around? I just found that, or I figured that nothing would really change. It would just, the colors of the currents would flip. The time in the real world is a little bit faster than computational model, and this might be improved by including some type of drag or air resistance, and also maybe something with the cardboard tube in the middle. And the shape of the velocity versus time plot tells us that the forces at the beginning are pulling the magnet down as the velocity is sharply decreasing, and then they go back and then they balance out, and then at the end they go back to sharply decreasing downward as the force due to gravity increases. So to the reflection questions, if the resistivity of the conductor were reduced almost to zero, the current in the loop due to from Ohm's law, you can see the current would increase greatly, and then that would result in the force on the magnet increasing to the point where the magnet would just stop in the tube and be equal. The force to the magnet would be, or the magnetic field would be equal to the force due to gravity. And if holes or slots were cut into the tube, this would affect the ring currents by making it harder for current to flow through the tube. And if a complete cut was made between the tube, then the current at the top of the tube would be split from the bottom of the tube, and then the effect of the braking force due to the tube would be greatly reduced. Thank you.